Hello friends, welcome to this lecture on the course of computer aided power system analysis. In the last lecture, we have looked into some examples of this weighted least square estimation technique, and from that example we have said that it is very difficult for us to recognize that which set of estimated values to be accepted, because as we already said that in the case of state estimation, what we would be doing, that we would be taking the measurements at a regular interval, and then with those measurements taken at regular intervals, we would be also estimating the states of the network or for the system at a regular interval. So, then therefore, just by looking at those values, we would not be able to recognize that which particular estimated values are really good enough for us. So, then we said that we need to do some kind of error analysis, or rather we need to do some kind of a statistical analysis on these estimated values as well as on this estimated error. So, then we would be able to find out that which set of measured values are really acceptable to us. So, then therefore, today we would be looking at the some aspect of this error analysis. Now, we recall that our estimated values x bar hat is given by x bar plus G inverse H transpose W into E, that we have already seen. So, then therefore, we said that x bar minus x hat bar is equal to G inverse H transpose W into E, it is the error vector. Now, if we take the expectation of x bar minus x, so what we get is that we get that G inverse H transpose W of expectation of E, and that we have said is equal to 0. So, then therefore, E of x hat bar is equal to 0. So, then therefore, E of x hat bar is equal to x. So, this we have already seen. So, we have said that this expected values of this estimated values we always converge to the true values. We also have seen that estimated errors is given by identity matrix minus H G inverse H transpose W into E, that we have already seen, and we therefore, we have said that expected values of the estimated errors would be I minus H G inverse H transpose into W into expected error, right. So, that would be 0. So, on in other words, we have taken that is equal to 0. Now, we have done up to this, and why have we done this? Because we assumed we have our basic assumption, which is a true assumption to a large extent, because this is due to the fact that errors are Gaussian with 0 mean. 0 mean means that expected value of errors would be is equal to 0, and we have already explained what is mean by this expected value of I mean what is mean by this expected, I mean why this particular 0 mean is assumed, that we have also explained. in some earlier class, and we also said that this measurements are independent of each other. So, this issue we today we need to look at in more detail. Measurements are independent to each other. Now, before we look into this issue in more detail, we need to recollect one very small thing. We also know that this expected or rather estimated value of error is actually given by z minus z hat. So, this is the actual true measurements and this is the estimated measurements. So, we again say that this is the true measurement. So, these are the true or rather the measured value we should say it is obtained measured values, should say obtained measured values, and this is the estimated values of the measured quantities. So, this we have already seen. Now, as expected value of is 0, so that means expected value of z minus z hat is also 0, or in other words expected value of is equal to z. Well, this is a trivial part. Now, let us look at the case of this independent in nature. Now, what is mean by independent measurements? Independent measurement means, now let us look, this is an important issue, independent measurements. Now, what is mean by independent measurements? We say that 2 meters are independent to each other. We say that 2 meters are independent to each other. 2 meters say ith and jth say are independent to each other, independent to each other if the expected value of EI EJ is equal to 0, where EI is the error associated with ith meter, EI is the error associated with the ith meter. Now, let us say that I have got now let there are m measurements. Now, we would be doing some generalized discussion. M measurements, m can be any value. So, then vector E would be E1, E2, EM transpose. So, then therefore, E transpose would be what? It would be E1, E2 up to EM, and E transpose would be E1, E2 up to EM. So, then therefore, this would be it will be something like this. It is E1 square, then E1 E2, then dot 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 E1 EM, then you have got E2 E1, E2 square, then dot 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 E2 EM. Then what we have is EM E1 EM E2 dot 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 EM square. So, this would be the matrix. So, this would be an M cross N matrix. So, this would be an M cross N matrix. This is M cross 1, this is 1 cross M. So, this is an M cross N matrix. Now, if I do take the expectation operator at both the sides, so then what I get? Now, if I take the expectation operator at both the side, so what I get? I get something like very interesting. So, I take expectation operator, and expectation of a matrix is nothing but now is essentially the elements of the expected value of a matrix is nothing but the expected value of the individual element. So, then it would be simply expected value of E1 square, then expected value of E1 E2, and then expected value of E1 EM. Then similarly, it would be expected value of E2 E1, expected value of E2 square, similarly expected value of E2 EM. Then it would be expected value of EM E1, it would be expected value of EM E2, and expected value of EM square. This would be the case. Now, we have said that all the meters are independent of each other. So, then therefore, if all the meters are independent to each other, if all the meters are independent to each other, then what we have from this basic definition, expected value of E I E j is equal to 0, that is for all I j is equal to 1 to m with an rider that I is not equal to j. So, in plain English, what does it mean? That all these off diagonals would be 0. So, E1 E2 would be 0, E2 1 would be 0. So, then all off diagonals would be 0. So, then therefore, expected value of would be essentially expected value of E1 square, then 0, all are 0, then 0, expected value of E2 square, then it is 0, then all are 0, and this is expected value of EM square. So, it would be a diagonal matrix. Now, what is meant by expected value of E1 square? If I do a simple analysis, all expected value of EI is equal to 0. So, then therefore, if I say that EI, if I say that expected value of EI, if I denote as mu I, so then therefore, mu I is equal to 0. So, then if this mean is 0, so then therefore, EI square is nothing but the standard deviation, or rather this variance, it is nothing but the variance, right. So, if this mu I is equal to 0, so then therefore, this expected value of EI square is nothing but the variance. So, then therefore, what happens is, so therefore, what happens is expected expected value of E transpose is nothing but variance 0 0 then 0 0 0 0 sigma m square, right. We call it matrix R. We call it matrix R. So, this is the matrix R, which is the basically the it is basically diagonal matrix in which all diagonal elements are nothing but the variance of individual meter. And also we said omega I, that is the 1 by sigma I square. So, then therefore, my wet matrices would be nothing but 1 by omega sigma 1 square 1 by sigma 2 square dot 1 by sigma m square, and all of diagonal terms are 0. So, then this and this is essentially R inverse. So, it is a very beautiful relation that my wet matrix is nothing but the inverse of this. So, wet matrix is nothing but the inverse of the variance matrix of all the meters. Of course, this is only true when the meters are assumed to be independent to each other. Yes, usually these are true, because usually these are true, but not always. But here we are, for the sake of simplification, we are assuming that these meters are independent to each other. So, then therefore, W is equal to R inverse. Now, we do something very interesting. Now, so far we have done E. Now, so far we have done we have computed expectation of E transpose, and that we have seen that this is nothing R. Now, we also have the estimated errors. So, now let us look at that what would be the expected value of this estimated error. Now, before I look that before we actually discuss it, let us first understand that what is the nature of this G matrix. G matrix is, that is the gain matrix, is given by H transpose W H. So, this is the gain matrix. The H matrix we have already seen, and please note that this particular W matrix is nothing but an diagonal matrix. Now, if I take G transpose, what I get H transpose W H whole of transpose. So, we get W H transpose into H transpose of transpose. So, therefore, H transpose W H. So, then therefore, this is G. So, then therefore, G transpose is equal to G. So, G is a symmetric matrix. Because G is a symmetric matrix, so then therefore, G inverse is also a symmetric matrix, because inverse of a symmetric matrix would be also a symmetric matrix. G is also a symmetric matrix. So, then therefore, G inverse would be is equal to G inverse T. So, this is a very important relation which we will utilize. So, this is very important relation which we will utilize. Now, what is we have already seen that expected value of errors is given by I minus H G inverse H transpose W into E. So, then therefore, what is E transpose? It would be E transpose into I minus H G inverse H transpose W into T, right. So, this would be the case. So, then therefore, we would now like to find out. So, what is, so then therefore, what is E transpose? So, it is I minus H G inverse H transpose W. So, H, what is this? H G inverse H transpose W, H G inverse H transpose W into E, and E transpose is E hat, sorry, E transpose into I minus H G inverse H transpose W into T. Now, what we have? So, now, so this is the expression. Now, I have to do some simple maths on it. Now, let us look that now what is, now let us look that what is H G inverse H transpose W T. This is I transpose is I, so minus H G inverse H T transpose T, right. So, let us say this is A. Now, if I say that it is A, if I say that is A, and if I say that is B, so it is A B transpose, it is B transpose A transpose. So, then therefore, it would be, so then therefore, I minus H transpose W T into H G inverse. So, then therefore, so which would be equal to I minus W is an diagonal matrix. So, it is W H, then it is G inverse into H transpose, and W is I minus R inverse H G inverse H transpose, right. So, this is the case. So, then therefore, I can say, so this is the case. So, then therefore, I can say that this into this is actually I minus H G inverse H transpose W into E into transpose into I minus R inverse H G inverse H transpose. If I take the expected value of both the sides, what I get? If I take the expected value at both the sides, I get is I minus H G inverse H transpose W. Then I get, because this is a constant matrix, then I get expected value into I minus R inverse H G inverse H transpose. This quantity we have just now shown that this quantity is R. So, then therefore, I minus H G inverse H transpose W into R into I minus R inverse H G inverse H transpose. So, then therefore, what I have got? We have got is expected value of E hat and E hat transpose is equal to I minus H G inverse H transpose W H G inverse H transpose W, and now what I do, I multiply, take this product of R with this. So, R into I is R. So, R into I is R minus R into R inverse is identity. So, then this goes H G inverse H transpose. So, this is H G inverse H transpose, right. So, then therefore, expected value of is now H I minus H G inverse H transpose W. Now, I take R common from both the side. So, I minus H G inverse H transpose R inverse into R. So, then therefore, it is I minus H G inverse H transpose W into I minus H G inverse H transpose W into R, as we have just now proved that W is equal to R inverse. So, then therefore, now if I do multiply everything, so what I get? Now, what is this quantity? This is an idempotent matrix. Now, I minus H G inverse H transpose W. Now, what is this quantity? I minus H G inverse H transpose W, that is equal to I minus H G inverse H transpose W, this into this minus this into this H G inverse H transpose W plus H G inverse H transpose W, that is this into this in the same order H G inverse H transpose W. So, we have just put this and this in the same order. Now, it is very interesting thing to look at that this quantity is nothing but G. So, then therefore, G into G inverse is equal to identity. So, then therefore, it becomes I minus H G inverse H transpose W minus H G inverse H transpose W plus H G inverse H G inverse, this is G into G inverse is I. So, this quantity, so then this term cancels out. So, this term cancels out H transpose W. So, this and this cancels out. So, this becomes I minus H G inverse H transpose W. So, then therefore, we have, so then what we have, expected value of E hat transpose is actually I minus H G inverse H transpose W into R. Now, because this into this is the same matrix, you see this matrix into this matrix is the actually same matrix. So, this is called an idempotent matrix. So, this is called an idempotent matrix. So, this is equal to R minus H G inverse H transpose. as W into R is equal to identity. So, this is a very important relation. So, what we ultimately found out, that we have very beautiful relation, that expected value of this error is equal to R minus H G inverse H transpose. So, then basically expected value of this estimated errors are not exactly equal to R, but it actually differs from the original matrix R. So, then therefore, this matrix plays a major role in our statistical analysis, and these issues we would be looking at in more detail in the subsequent lectures. Thank you.